Welcome to the closing seminar of our Arbor workshop on neural signal acquisition. Over the past week, students from 8 countries across Latin America learned to build their own biosignal acquisition system using the Arduino environment and how to use the bonsai software to perform behavioral experiments for neuroscience. This remote hands-on workshop, including this seminar, are taking place thanks to the generous support of the International Brain Research Organization, the Argentine Society for Neuroscience Research, and the Metropolitan Fund of the City of Buenos Aires. In today's talk, we have 2 amazing speakers that passionately disseminate neuroscience and open source tools around the globe, sparking this flame in many people, including myself. We hope that by sharing their experience and insight, you too will be inspired and expand this even further. It is our pleasure to have André, Maia, Chagas, and Tim Marzullo here today. Thank you so much for accepting our invitation, and thank you, Tim, for agreeing to speak so late, and even on your birthday. We will hear the speakers first and then have a discussion at the end. So please feel free to write the questions in the chat here in Zoom or over on YouTube, or you can raise your virtual hand so you can take a turn to speak. In Spanish, por favor, no duden en hacer preguntas para los oradores en español o en inglés, según se sientan cómodos, en el chat o levantando la mano virtualmente para usar el micrófono. So first, let me introduce André, Maia, Chagas. André is passionate about open science and open source hardware, and how those two can be used to increase research and education research around the world. He has a background in neuroscience and has been developing affordable open science hardware and teaching others to do so via workshops, talks, and outreach events. He started Open Neuroscience and volunteers at Trend in Africa as an open source advisor and by organizing and running open labware workshops. Currently, he works at the Department of Neuroscience in the University of Sussex, where he develops equipment to support research labs. In his spare time, he offers consultancy services around open science hardware through Prometheus Science. Please, André, you can go ahead now. Thank you for being here.
Thank you, Cecilia, for the introduction. Thank you for the kind invitation to present some of the work we do. Thank you, everybody, for joining us so early, whatever you are, or so late, whatever you are. Let me just start by sharing my screen. Sorry, just a second. There we go. So hopefully you can see my presentation now. Yeah, okay, cool. So I'm just what I want to talk about today is a little bit of the work we do on open labware and how you can leverage basically open source hardware for the development of science and for science just in general, right? So, I mean, Cecilia already presented what I do, so I won't spend too much time on this, but basically all of the work and all of these different hats that I'm wearing, they're all put together via open hardware. And I would like to start by sharing, like, just giving a step back before we talk about, or just a step back to remind us that everything we do in research and academia is basically public money, right? So you get taxpayer money that gets converted into a grant. If you're lucky, after you wrote many proposals, you get this grant, which is going to pay for a bunch of different things. And with a lot of sweat, blood, and tears, you hopefully get publications, drugs, treatments, and new technology out in let's say, in a prototype stage, right? And this is where I think a lot of the problem begins, because universities are not equipped or set up to actually bring these things to market, right? Or to make them broadly available. And so what happens nowadays is that they basically take these things that were created with public money, and via license agreements with patents or copyrights or whatever it is, there is a technology transfer to the private sector, but then only a few companies, one or a handful of companies, are able to access this and make it commercial, right? Of course, they add a lot of value by making this commercially available, whatever it is, but then it also leads to high costs and the public ends up paying, let's say, twice for all of this, right? And so one example, for instance, are microscopes. So microscopes are a technology from the 17th century, right? The modern microscope as we know it. And you can see in this image here on the right side, or at least on my right side, I don't know which side this is presented to you on your screen. it's basically the same format of a 1920s microscope. So it didn't change much. Of course, the optics got much better. There's more electronics and cameras to record everything, but the technology is pretty much the same from the 17th century. Still, this costs 10,000 pounds. It's only produced by a handful of companies in Europe, in the US, maybe Japan, right? Or distributors in these places. And they're only built for these environments which have like a certain temperature and humidity and so on. Right, and so let's say you are in Brazil, where I'm from, or you are in Argentina, or you are in a place in Africa where I worked a lot. You get the money to buy one of these. It starts working in your lab. It's wonderful. 6 months in, maybe like something breaks because of the humidity, something rusts or whatever. You don't have the opportunity to actually get it repaired because there is no one around that is licensed or authorized to open this, and you don't want anybody tinkering with a £10,000 piece of equipment, right? And so this has a very high cost. There's only a few distributors. You don't want to change this all the time to your new experiments because it's really expensive. And the companies providing this, they don't have an economical interest of making new versions of this all the time, right? Because like they just make one model and sell it for many years and people have to buy it. And so this is where, for me, enters the whole idea of open source hardware. So even though we have a supply chain that works for equipment where like you can just buy things, it doesn't work for everybody. And because these are all black boxes, you don't have the opportunity to change them. So this is where open source hardware comes in. So the idea of open source and open source hardware is just putting a working framework, let's say, onto something we humans have always done. So we always shared things, right? So if I like to cook, I share recipes with my friends and family, and then I share my book, and then they copy it, and then they make their own. So I make a cake. They like to add raisins. They just made the first derivative of my cake, right? It's now a cake with raisins. We both won. We both know now that the original recipe of the cake works, and the cake with raisins also works, and they're both delicious, and so on. The whole idea of open source is to leverage these things that we've always done as humans, but put a framework around it so that people have an idea on how to share things, what is allowed, what is not allowed, and how to do it, right? And so here is just, I mean, I shared the links for this slide, so I think the organizers are going to share with you afterwards. But basically, everything you create in hardware and lab equipment is shared using specific licenses, right? And this makes reproducibility around the world and the replicability of science much better as well. So here are some examples of open source microscopes. There are many, many projects. It's just 4 of them that I like particularly. And so on the top left side here on where you see this little, this is a flypie, something that we built, and we're going to talk a little bit more about it as an example. But what most of them have in common, other than being open source, is that they are a fraction of the cost of commercially available tools. Each of them is really custom to a specific function, right? And here on the bottom right, this is a mini scope, which you might have heard of during the talk from Jakob, and so on. And these things are really like a really tiny microscope that goes into the head of the animal. And they're really wonderful, and they're still like really complex and open source, right? And so by being open source, all of the designs of these things are online, so you could build it today if you wanted. They're all like much cheaper to build. So the 3 ones, other than the miniscope, they're all under $200, right? And it's easy to modify them. And because we're sharing the designs, you can see all of the components, and you can supply things locally and substitute things that you don't have the original thing in the design. You could, because you know how it works, because of the design, you can substitute that for something that you have available locally, which makes the whole thing way more robust to supply chain problems, right? I spoke about the flypie, and this is something that we published. So here, just to make the point that like leveraging and insisting on open source and developing open source things doesn't kill your academic career. It can actually lead you to papers and methods papers, right? And this was published, I think, in 2015 now. This is actually getting old. We should come out with a new funky idea soon. But basically, this was when we published this, and we showed that with $100 worth of components, you can actually do a lot of decent imaging, right? So you can do, here on the top left, you can see parasites that are present when you drink water that hasn't been treated. On the right side, you can actually see a fresh cut of a pyramidal neuron. And then on the bottom, you can see the vascular system of a zebrafish larvae. And then we also showed that you can do like more fancy methods like calcium imaging on the left side and fluorescence imaging on the right side. Right, like this is the long story short of this thing. I think more importantly than this paper for us was the fact that we can show, I jumped one slide, but basically, as I said, right, like we build this with off-the-shelf components, 3D printed parts, and if you put all of the capabilities that we build into this, and you would buy individual equipment for it, you would spend easily worth more than 50,000 pounds of equipment, right? And so this allows you a couple of things. The first thing is that you can build several of these, still save a lot of money, and really reduce the amount of time that you need to do one data collection round, right? So here on the right side, you can see many of these other microscopes, which are called PySpies. They were actually inspired by the FlyPy. And so in this image, I want to make these 2 points. Somebody derived our model and made something for their own, right? And so they made something that was actually, in this case, fine-tuned to tracking ants. And they made a massive parallel rig where they have, 1, 2, 3, 4, 5, 6, 7, 8, and then another 8 at the bottom, 16 rigs running in parallel, right? And so data collection here is much, much faster than if you had one microscope, right? We know of like more than 80 units of the FlyPy being built and developed by different people around the world. And then if you think about like the savings that I mentioned, like if you only consider one microscope for 10,000 pounds, if you have 80 of these units for 100 pounds, you can do the math and see how much money people have saved in doing experiments with these tools. And this, of course, is just one example of open source hardware. There are many others, right? But I think what I wanted to drill down now is the point that we actually started using the FlyPy initially as a tool for teaching. So we started teaching people with Trend in Africa how to build these FlyPys to do their own research. And then we derived for something a little bit more complex, which was how do you leverage open source technologies to build your own lab equipment, right? And so basically we've been doing these workshops for a while now. And just to show you some videos, if they're going to show, but this is basically the end of one of our workshops. And what you can see on the left side is somebody actually, let me just stop the one on the right. On the left side is somebody who built a micro manipulator. They just reproduced something, but you need to remember that these groups started this workshop without knowing anything about electronics or 3D printing or anything. And they spend the 2 weeks learning about all of this. And in the end, they have a working prototype of something. I just want to show, here is somebody who's explaining how they built this and an actual working, let me see if I find it, yeah. So this is an injection system that they built, right, using servo motors and 3D printed parts. And they adapted something actually that I think Tim developed the first manipulator, and then we derived something out of it, and these guys derived actually something for injections with this continuous servo motor, right? And then here he's just explaining how it works and so on. And then on the right side, we have something which is an avoidance box, which is the first prototype. And basically you just see the little hatch on the door moving up and down. But this is all built on Arduinos, which we have been learning during this workshop. So we've been conducting something kind of similar in different places in Africa over the years, right? And so we've been doing like a lot of these workshops in different parts of the world. And this is one of the things where we wrote grants and we got support for and so on. So this was also good for our career. So again, the point of, if you're an early career researcher, this is not a waste of time. This is not something that is gonna, like, oh, I won't be able to do like my data analysis or my experiments, but rather something that you can definitely like invest in as a good thing for your career, right? Something that makes me really proud is that we've been fine-tuning all of these open labware workshops over the years. And I think now the way we teach it, it has gone to a point where people can really leverage what they learn and actually start building their own solutions. So here I'm just showing one example of a group in Ghana that participated in one of the workshops. And actually, after leaving the workshop with a working prototype, they actually went on and published an activity box for mice that they built on their own. And so now, if you think about this in the long term, and in the dream point of view of this, is there is technology that is Ghanaian, that is locally built, the knowledge is there, and even they could, if they wanted to start a company to build and supply these boxes to the local neuroscience community, right? And so in a way, I think what we've been trying to do with Trend is like teaching people how to build fishing rods, right? And not teaching people how to fish, but rather like how can they build their own tools for their own environments, and how can they have these tools then help them improve and do data collection and improve their own research systems. This is another example from another group that was in the workshops. Basically, this paper is not describing a tool itself, but on the paper, you can see that they use an Arduino and they build their own stimulation system to do this paper. And so these are like two very cool outputs that we have from the workshops. We do know that there is another paper in the pipeline from another group. So hopefully in my next presentation, there will be one more example to share. And I'm really hoping that this is then taking place and taking hold in these places in Africa. We also published in the beginning of the pandemic in April, a paper doing a review on all of the open hardware initiatives, building tools to fight COVID, personal protection equipment, respirators, sanitizing units, sterilization hoods, and so on. Together with some colleagues in Africa, I worked together with them remotely, mostly like trying to help them online with questions and suggestions and so on, but they basically went on and bought a 3D printer and built over 400 face shields and face masks based on open source designs that were online, right? And this came out as a preprint, and we just submitted a paper describing this for review. So again, the idea of open source hardware is something that is much, much faster to innovate, to respond to issues, and to do things that are even outside of research, right? And so just to show you, like it's not an isolated case from our working groups, right? Like there has been what I'm calling a Cambrian explosion of papers. So what you're seeing in this image is we did a PubMed search with all of the papers containing open source hardware, either in the abstract or derivatives of this, like open hardware, open labware, open science hardware, or whatever, right? And of course, there are a very, very tiny fraction of all papers in PubMed, but you can see over the years how this curve is accelerating, right? And so like open source hardware, from where I see it, is here to stay in research. So the primer that you've been having with this workshop is really a fantastic opportunity to hop onto this moving train, and hopefully you start developing your own tools or integrating with the existing community. These are just some examples of things that are available. They are everything from robots that actually pipette Drosophila food to things that measure your heart rate and the curve of your heartbeats and so on. And this is always available online. So really, you don't really have to start a project from scratch, right? So you can simply find a project, start collaborating with them, or derive for whatever you need and so on. And so to make life easier for everybody, there is another project that I'm going to briefly mention, which is Open Neuroscience, which is a collection of open source tools for neuroscience. So if you excuse me for a minute, I would just like to show you, can you see the Open Neuroscience page now? So this is actually something that I collaborate with a group of people, and Cecilia, who's organizing this workshop, is one of them. But basically what this is a website where people can fill out a form that we prepared about their projects, and then we just do a quick check for spam, and then their projects go online, right? So you can see here, these are just the list of projects. There are more than 100 projects now listed on Open Neuroscience from everything, right, in neuroscience. So if you want animal electrophysiology, you can filter that out, then you're going to see backyard brains, which you're going to hear all about it in a bit. If you are more into, let's say, optogenetics, then you can see all of these projects that are related to optogenetics, or if prosthetics are your thing, they're also, and so it's easy to filter. Maybe you heard about something and you want to search for, I don't know, photometry, right? And so then you're going to find everything that is related to photometry, right? So not only they're filterable, but they're also searchable. And a little shout out to the team that makes this happen. Without them, this wouldn't be at this stage, and because this is a project that I started back in 2013, I think, and it was like me painstakingly putting project one by one. When people started collaborating and we flipped everything on its head, and now people can they can fill out the form and put on their own projects. We're also running a seminar series, where people have been talking about open source tools for neuroscience. And actually, Tim, if you want, at some point, we should schedule a talk from Backyard Brains in our seminar series. It will be wonderful to have you guys, yes. And so you can see that there are already like more than 20 projects, and some of them have like 300 views and so on. But it's just like people talking about the tools that they developed, right? And so it's a really good start. If you want to learn about a certain tool, it's normally like half an hour talk, and then people basically have questions afterwards. So it's really something that is nice to do. The next one is actually next Wednesday at 3 o'clock UTC. So So if you like open neuroscience and you have a project that you'd like to contribute, like just fill out our form. As I said, these slides are going to be shared. And you can also just send us an email. And so I don't want to go over too much in time, but there is something that I wanted to show, which is just like the last point. So there was this is the second of review that talks about this from the same person, from this researcher, Joshua Pierce, where he's showing the amount of savings that there could be if research institutions and grant-making agencies were investing in open source technologies, where we would be saving at least 87% when compared to the development of proprietary tools, plus all of the benefits that I mentioned in terms of replicability, modularity, customization, and education purposes, right? And And just to give you an idea in numbers, this is from the Miniscope team that I mentioned. They built like 2,500 Miniscopes since they began, and they estimated they saved already like $200 million in public funding, which could be used for other more useful things other than just paying off a company that is making like a very big profit out of something that was created by the public. Right, and then he goes on to say that all the papers that come out from Miniscope are in par with whatever is using proprietary tools as well. So it's not the case that if you're using open source tools, you're not going to be able to collect the same quality of data. On the contrary, right? And so here I just put some links that are useful because you're going to get access to the slides. And with that, I would like to say thank you. And I guess now you're going to save questions to the end of the thing, but you can definitely reach out to me on Twitter and via email as well. I'm more than happy to start conversations about all things open source hardware. Thank you.
Thank you, André. Thank you so much for all that, that perspective and all the information. And I think the economic aspect is something that we haven't touched upon yet. So that was super interesting to have concrete examples about that, so to learn from that and discuss at the end. So now we're going to move to Tim's talk. Tim is a professional neuroscientist dedicated to improving public understanding of how the brain works. In early 2009, he co-founded Backyard Brains, whose motto is neuroscience for everyone, by designing and making inexpensive equipment and experiments that allow scientists of all ages to study and comprehend the electrical activity of the brain, muscles, and heart. Today, the equipment of Backyard Brains is in 99 countries around the world. He also works in education, teaching classes on neuroscience, invention, and creativity in the scientific process, principally in the United States, Latin America, and South Korea. Thank you, Tim. Please go ahead. Actually, you're muted now, Tim. Sorry.
Thank you, Cecilia. Muchas gracias por la invitación. Estoy feliz para participar en este congreso porque yo viví en Chile por 7 años y medio y hice muchos amistades con muchos científicos y científicas Corea. So I'm going to speak in English, but feel free to ask questions in Spanish. I miss speaking Spanish, and you know, my Korean is a lot worse than my English and Spanish. So I'll just go into my talk here. So one moment. Okay. Sure. All right. All right. So un momentito. All right. So November 5th, mi cumpleaños. Okay. So in this talk, I'm going to talk about open source. André gave many good examples with his fantastic group over there of inventions they have made. And the important thing is that it can be considered kind of hip, like to say you're open source, but it's not really open source unless it's effectively documented. So I'm going to talk a little bit about that in this talk. Okay, so the motivation for Backyard Brains, you know, is because we love studying the brain, and also there's a lot of you know, health conditions that affect the brain that we don't really have effective treatments for. And the mission of Backyard Brains not only is to disseminate knowledge about the brain, it's actually to accelerate the field. And one way you accelerate the field is you make the tools more available to people all around the world at all levels of education. So that's really the mission of Backyard Brains, that you don't have to get a PhD to study the brain. You can study it at the elementary school level if you want, you know, because we've always been jealous by other fields such as astronomy and mathematics and electronics, where, you know, I have friends who are electrical engineers who were playing with electronics when they were 13, but I had to wait until I was in grad school to start doing neuroscience experiments. It's not fair, you know. This is the equipment that I did the majority of my research work on. It was a high channel Plexon electrophysiology system that cost $250,000. It was in a special locked room. You needed a special key, and the software was kind of hard to use. You often had to program the devices yourself. So it's just it's a fancy, complicated scientific instrument that, you know, in 20 years, they sold 500 of them or something like that, you know? So, but Backyard Brains has been working, and now, you know, we have kind of single channel versions that fit in the toolbox that we ship around the world, and we're quite happy with that. And the philosophy of open source is really to improve access of equipment to people. So we were inspired by the computer revolution because, you know, there were computers that you could use in the 60s, but they were at a University of Michigan, Stanford University, MIT, University of Cambridge. You had to have a special access, special permission, special key, you know. But then when the Altair came out in the late 70s, and suddenly normal, quote unquote, normal people could use computers, now we know we live in this telecom revolution, you know, that was changing every day. All right. Okay, so if you want to start building, you know, your own kind of laboratory and doing your own kind of open source inventions, you don't have to do it at a university. You can build your own lab. So this is an example of a lab I built in the basement of the house I was living in at the time. And you can see it looks like a mess, but you can see an oscilloscope on the left. You can see electrical components on the right, tripod set up to document the experiments, the decks, you know, all kinds of stuff, you know. And so I can't really do experiments on mammals because I'm not a university, but you can do experiments on invertebrates, you can do experiments on plants, and then you can do non-invasive experiments on humans. So you can do all kinds of science just in your own house, you know. And this is not like I was some rich dude. This is like when I was a grad student, I'd spend $50 to $100 a month on this tool or that tool, and then, you know, after a couple of years, I had a pretty good lab, you know. So if you want amateurs, you know, to contribute to science, amateurs have. So you can notice in the upper left, those are the famous Paleolithic artwork discovered by a group of French teenagers in France in I think the 1800s. On the right is the Hale-Bopp comet, which was co-discovered by a professional and an amateur. And on the lower right is a German border collie that was taught 300 individual words by a pet owner, and it became a science paper that she published with a professional academic. Okay, so you can do kind of electrophysiology on your own using open source tools, principally in invertebrate physiology, as Backyard Brains does, human physiology, and also plants, which is what we're getting into now. Okay, and so if you want to get into this kind of field and you don't really know how to do it, what you do is you participate in conferences like the one we're doing right now, and also you can go to maker spaces. So Backyard Braids is very proud. Estábamos muy orgullosos because we were the first members of the first makerspace in all of South America. This is the Santiago makerspace. It was full of engineers and designers and creative people, and just surrounding yourself with creative people is really a way that projects find a way of getting done, and also you can generate a lot of amazing ideas. This is a picture of the Arbor makerspace, all hands active, of which we were highly active in as well. Okay. So if you want to build your home lab, these are the kind of the equipments you need. You low microscope, which André certainly talked about. Building up an electronics library is relatively easy. You've been doing that all week, and some basic test equipment. And with that, you can actually do quite a lot. Again, one of the biggest missions of Backyard Brains is you don't need to have access to a world-class university to do cutting-edge science. The mission of Backyard Brains is that education is a circle. So high school students can work with university students, can work with grad students, can work with high school students. So there's like more transparency between all the institutions. So. All right. So yeah, I don't know. I'm going to talk about that. I need to talk about that. All right. So this was a collaboration that we did with André and Todd Baden. We designed a 3D manipulator. You see it's a 3D manipulator made in Google SketchUp. Then we used a MakerBot to build it. You can see it right there. And then turned it, then Baden and his group modified it, and it became a publication. And it's a very highly cited publication. It's my most cited publication. And it's like, and I just had such a small part of that paper. Oh well. Okay. So if you want to open source your invention, right? Like you want to say, I'm open source. I'm part of the community. I hang out with André. I hang out with Cecilia. They're my people. I'm open source too. Yeah. So if you want to be like, you have to document it, right? So labs are full of inventions. You all are scientists. You invent things in your lab all the time. So this is an example of a simple two-stage amplifier. I could just throw this on the internet and say, look, I'm open source. I shared the proto board. And yeah, I guess people could see this proto board and rebuild the invention themselves, but it'd be easier if you actually improve the documentation. So then we have all open source on our website. We have the actual special sauce. You could actually build, the spiker bots with this diagram. We actually have all the mathematics for how it works. You can see it's 3 chips, and with this you can build a spiker bots. You can even go deeper than that and actually share your Gerber files. So this is the actual digital electronic file that you send to the factory, and then you get the circuit boards back, right? And so we actually, like André said, one of the advantages of inventing equipment is if the invention works, if it meets a spec, and you just document how it works and how you built it. The publications are not terribly difficult. Their views don't tend to be very harsh, because if the invention works and it's novel, it should be shared with the scientific community. So as you all are finishing your graduate work, just remember that when you're doing your graduate work, you invented something. You invented something to do your unique experiment, right? So you can actually make a chapter of your dissertation the invention that you had to make to do your experiments, and then you can actually publish that, and that invention you made might actually be more useful to the scientific community than the actual experiments you did, because the same thing happened to me with Backyard Brains. That Backyard Brains wasn't part of my graduate work. It was a side project, but people were way more interested in this side project, making low-cost neuroscience equipment, than all the, hundreds of experiments I did with rats over my entire grad school career. But hey, you respond to the community, and I'm happy with what I do right now, okay? Okay, so when we say you must document your invention, right? So in the publication we had on the spiker box, you can see we have all the building files, all the materials you need, and actually the cost of analysis actually building the invention. So this is an example citing our work of how to properly document and share your invention. Right? Okay, and I get really emotional whenever I see this picture. It almost makes me cry. So these are university students in Iran. So Backyard Brains, as a U.S. company, cannot ship to Iran because of the politics and the trade embargo. So we cannot ship equipment to Iran. But because we're open source, they just downloaded all the schematics, and it's like an Iranian Backyard Brains. They downloaded all schematics, and you can see right there they built their own Iran version of the spiker box to like do their own experiments. It's amazing, you know. It's very rewarding to see a picture like that. You know, we surpassed politics, you know. So there it is. Yeah, there's the Backyard Brains Iranian spiker box. All right. Okay. Yeah. So anyway, like the manipulator that we built, you know, very careful about having all the instructions for how to build it, which is why when Todd and Baden saw it, he was able to modify it so quickly and then resulted in a publication. Right. And even on our website, where we actually sell these things as products, you know, our business sustains itself by grants, right? By educational services and also by selling hardware. And even like very odd for a hardware company, not odd anymore. You met Jacob Pope and the Open eBiz guys. You could actually build all our machines without even just by downloading the files on our website. Okay, there's that paper. Okay, and there's the Tom one we did with Tom Baden. And over time, we've been getting into microscopy as well. So here's an example of a cell phone-based microscope. It's got a simple lens with a camera. You see right there what we built. And then on our website, we have the laser cut file for how to build it yourself. And actually very recently, in March, I published a paper with a Chilean colleague, Maia, Universidad de Chile, because before the conference started, André and I were talking about how to build your own 2-photon microscopes. And luckily with electronics have become so inexpensive that you can prototype with electronics very rapidly, which is why Backyard Brains was able to exist. But it'd be hard to make, someone raised their hand, someone had a question? Oh, Jose.
Go ahead, Jose. Maybe it was unprompted.
Yeah. Voy a seguir, y si él quiere hablar, dale nomás, okay? So this was with a colleague from the Universidad de Chile. You know, you can build an amplifier from scratch, but you can't really build a microscope from scratch. You know, Manu Prakash has done amazing work with the Stanford group with a Foldscope, but it was kind of frustrating when I would read the press about it. And he's a colleague of ours. I'm not criticizing him, but what the press would say, he's built a microscope out of paper. And I'm like, I remember first reading about that. I'm like, what's he doing? Is there like some weird stuff with the diffraction of the light between slits that's somehow achieving magnification? No, it's just like the structure of the microscope is made out of paper, but the lens is still made out of glass. It's not a microscope made out of paper. It's like a microscope that includes paper in it. You know what I mean? So, and so like I wanted to make a microscope where you're actually manipulating the glass yourself. So we actually built a protocol para alumnos in Chile where you can actually melt small bits of glass into spheres and kind of insert it into an apparatus, and you built a microscope from scratch. All right. So you can see you can actually break glass just in your kitchen, or you can buy glass, or if you can actually buy fancy jewelry, Swarovski jewelry, and melt it if you want a higher index of refraction because it's crystal glass. So then you can see we melt the glass and we put it in this little thing, and then you can see in the lower right we have motor cortex neurons. And this is a microscope built from scratch by literally melting a piece of broken glass from a drinking glass, a wine glass in your kitchen, right? All right, so you can see these examples of the magnification we achieved. And so we've actually done this. You know, André talked a lot about teaching people how to build tools. And so students would love building their own microscopes. And if they actually built one themselves that had a really good image, they would then take a picture and post it on Instagram. So that tells you that they enjoyed the activity if they're flexing on the gram with their microscopes. You know, it's an example of student work. Okay, and so we like André, we've been delving into microscopy. This is a more sophisticated microscope we did with Católica and Cambridge, doing a fluorescence microscope. we designed the housing, and they did all the genetics. So you can see this is some of the data, and again, we have the complete assembly instructions in the supplemental files, and I think 100 have been built. We can't drop those numbers like André can, but other people have built these things. We're pretty proud of that. Okay. And so here's some examples of good documentation. You all are playing with Arduinos in this class. And Arduino is just like the gold standard for effective documentation, right? You can go on their website. It's very easy. It's very easy to navigate. I'm a horrible coder. My electrical engineering friends make fun of me with love because I'm such a bad coder, but I learned how to code Arduino on a Saturday afternoon because it's very well designed and it's right on there, right? Okay, and then it's built. High school students can work on it. This is a Chilean, Lucas Alvarez, who invented our first Arduino interface where you can control lights by flexing your arm muscles. This is an example of bad open source. I've always wanted to play with software-defined radio. It seemed kind of cool. Like it just records a broad antenna that records all the signals, and you can play with it. And I bought this thing, and it was $400. And I consider myself a fairly intelligent person. And I was on the website, and after a week, I gave up. I just felt like the documentation was so horrible. Like there was no documentation on how to use the thing. You had to be a coder and already know how to access the hardware. So they're trying to use the open source thing, to sound cool, but their documentation is so bad. I basically gave them $400, and I had this brick in my lab that I couldn't use. Okay. Yeah, it's horrible documentation. So anyway. There's some new stuff. Deep Lab Cut, is very popular, which you guys have been using. They have built a very good community, and they are improving their documentation on how to use it. So these are like Tim's. You're not supposed to read to your audience because I know ustedes son muy inteligentes. Ustedes pueden leer en ambos español, inglés. But this is like, so it's discúlpame. These are like the 4 Tim rules of open source. If another person needs to be able to build it, if it's so complicated that only you can build it, it's not really open source, right? Other people should be able to modify it. So, I'm Tom Baden modifying our manipulator to have motors and everything, right? And you should publish it as well, right? Okay. Right. And so the nice thing about open source hardware is you tend to make a lot of friends. It tends to allow you to build careers, right? So this is the second time André and I have given a talk. I gave a talk for another conference, and then Cecilia invited me. So sharing your tools actually builds friendships, and friendships are what make life worth living. Perdón si yo sueño corsi, perdóname. Okay, all right. And like André said, this field is growing quite rapidly, and the cost of scientific equipment is going down. And really, the only cost to doing good science should be your time, right, and your creativity, not the I'd love to do this experiment, but I don't have the equipment and I don't know how to build it. We're working to change that right now. So stay curious, y'all. Thank you for your time, and André and I will be happy to answer questions. And more importantly, we want to see what you invent in the years to come. So we challenge you to invent something that makes our work look horrible. All right. Ciao, ciao. Thank you.
This is great. Thank you so much. I think it's super great ideas for everyone, and so much positivity, and how to also the practical aspects, right? How to leverage that for your academic career is also an important aspect to keep in the back of the mind. Anyone, if you have any questions, please, you can raise your hands. Otherwise, I'll start and ask both of you. You've worked with so many people and so many different places and at different levels, right? So what are the commonalities, or what are the takeaways that you have learned from working with so many people? And maybe what are the challenges, right? If you can also touch on that. It's a very broad question, just to start the conversation.
I'll let you get started, André.
Okay, cool. So I think the common thing, and this is something that I learned over the years, and I guess this is, I don't know why exactly, but people are super capable, right? Like in our cases, right? Like we go to places to give a workshop on something that they never heard before. And it's also your case, right? Like you've been working on these things that might be completely new for over a week, and you've been getting like bombarded with information and so on. And you're going to absorb a lot of it and so on. In our cases, people have been learning, and it's all like whatever people were not able to learn, I personally take it that it was our fault in not being able to teach it in the proper way, so to say, right? I don't know if that makes sense, but basically like people are really capable, and it's just a matter of like translating the knowledge you have into a reality or to a setting that they're able to quickly grasp it. Like what Tim said about the Arduino, where they documented so well that somebody that has never seen electronics can learn it in an afternoon. This is like a gold standard of like how they broke the barrier of learning something, right? And I think the challenges, at least in our case, is always an infrastructural challenge. So a lot of places in Africa, like you, sometimes there are like power cuts over a couple of days. And so if you are there to give a 2-week workshop, and like 3 or 4 days of the 2-week workshop, there is no power, then like you need to figure something out, right? And then solutions have been like put up a solar panel, like hire a company, put up like use some of the grants and put up a solar panel. And then there is a room now in the university which has solar powered 3D printers, right? Which is quite cool as well. And so, yeah, I think that's all I can say about this. Sorry.
Yeah, we haven't really seen that many difficulties. The only difficult thing is sometimes getting access to electrical components can be difficult. You know, in Chile, there's a place called Casa Real, which is like an electronics store where we would buy components. In Korea, there's an electronics district. But if a country doesn't necessarily have an electronics district, then it can be hard to find the chips. And depending also on the customs policies, it can be hard to ship electronics to other countries. It's like there's like some weird. People think like you could have like literally a piece of trash, piece of electronics, like a little soldered board with one chip on it, and depending on the country you're in, customs thinks you're shipping an iPhone, and so they want to know what it is and how much it costs. It's like, look at this thing, it's trash. Then that can be frustrating, being a hardware company, because sometimes getting hardware across borders can be a challenge.
Yeah, we dealt with that, having to send our kids to everyone in different places in Latin America, and so many different regulations and stuff. Yeah. So yeah, anyway, I want to give space to any students. I would like to.
I have a question. I will be like advocating for the devil a little bit here, but what are the bad side of working open in your experience? Or the bad experiences of work, if there are any? Maybe you say no, it's all great. That's also okay.
So I don't wanna this sound like too romantic, but honestly, ever since committing like to fully open, the only thing I've noticed is that I've dropped a lot of like silly worries, you know, like, oh, I'm gonna get scooped, or if people see my work too early, they're gonna beat me to it, and blah blah blah. And like this never happened, right? And normally it's because people don't care. Like if you put something on, I mean, and at least until it is published in a paper, right, and it's been peer reviewed and so on, people generally don't care that you have something on GitHub somewhere, right? And so, for instance, I can share with you, like all the work we do is open source from the get-go, right? So if you go onto this link that I'm sharing on the chat, you're going to find everything that is being developed here in the department right now, right? And a lot of it is still in like very prototypical stage, and a lot of it could be, oh, like people are going to steal our idea. Like this doesn't matter, like nobody cares, right? And at least with me, this never happened, and I might just have been lucky enough. But this is the same that I get from other people. Like, yeah, you know, like it was there for like 10 years before anybody noticed it, or until we got it published somewhere and so on, or we made an effort to advertise it. And so like you really like just stop with the silly thing of like, oh, it's my science, it's secret and so on. And you start focusing on like having more ideas and developing other projects and so on and so on and so on, right? At least from my side. The only pushback that I got was like from older academics that said, oh, this, like, you're just playing with plastic stuff, right? But I think that they're just on the wrong side of history, to be honest.
Yeah, I can give a commentary as a company, because whenever we're trying to raise money to, you know, build a team to work on new experiments or work on a new prototype, we're always asked if we have patents. We say we don't have patents, we're open source. I'm not going to pay a patent lawyer $40,000 just so I can, like, what is even a patent? Like, means permission in Spanish, but it's permission to sell this invention. It's kind of silly. But I think the backyard brains market of neuroscience education is niche. So it's sufficientemente niche that there's not really a risk of someone directly. We have competition, but someone just like ripping our designs and just reselling them. That did happen to MakerBot. So MakerBot was a 3D printing company, but the market for 3D printers was so big that once they started getting all this attention and they were open source, they started seeing a lot of clones come out. We don't have that problem because we're not that big yet. Maybe if we get that big, that's a problem. That's something we have to think about. We don't want to think about it right now. And so that's like a serious bad side, but that doesn't affect us. And kind of the funny bad side is we have a popular invention called the human-human interface, where when you flex your arm, it simulates the arm of another person. It's kind of a funny, like, nerdy neuroscience toy. And we have an office in Serbia, and a couple coders in Serbia and some engineers in Serbia that work out of there. And our chief coder went to like a maker space where you show off your inventions to other makers and ask for suggestions. And this 16-year-old kid had this like invention. It was just in a generic black box. And he said it's when you record the muscles of one person, it stimulates the nerves of another person. And Stanislav said, wait, that sounds like the backyard brains invention. And when he kept pressing it, he realized that the teenager had just taken a human-human interface, put it in a black box, and made ports and said it was his invention. And of course, like, that's so innocent. It doesn't really affect us. It's kind of cute, actually, you know.
Thanks.
Sorry, may I just make a comment to the 3D printing thing? Yeah, so MakerBot was definitely an example, and they had like all sorts of trouble for them closing their printer, right? But then nowadays you have Prusa, which is also an open source company, and they also get cloned. And I just want to make the comment that I think what they get their benefit from is that they offer like excellent customer service, and they keep innovating in the market, right? And so it really drives them to be like aggressively innovating. And so, of course, I don't have a company in the sense that you guys have a company. Like the consulting that I do is not the same as the company that you are actually offering products. And so I don't know exactly the pains that you're going through, but my point is just like, there is now examples in the market where you do have a company that sells things that are being heavily cloned, but they're still like killing it, right? Like Prusa is still like one of the best printers in the market, and they're making like a lot of revenue as far as I know.
Yeah. So we just have to be more innovative than others, and that should be the driving force.
So Veronica, if you'd like to go ahead.
Yes, I have one question. So thank you very much for these great talks. They were enlightening. I am just a user, not a developer, so who knows, maybe in the future. And I was wondering what happens with the publications, because I suppose that you want what you develop, you want it to be open to everyone in terms of the journals. I mean, you know that there are journals that they aren't open. People have to pay to read those papers, and on the other side you have like open journals where people can have free access. And I can imagine that you prefer the open journals, but then you have the problem that you have to pay a lot to publish in those journals. And I just was wondering, like, what are your thoughts about this? And maybe if you just don't really care about those publications. I believe that the publications in the journals are relevant because the scientific systems ask you for papers. But maybe if you just put your development in a website organized, maybe you're just happy with that. So I wanted to ask you about that.
All right, sure, I'll start this time. So Backyard Brains only publishes in open access journals. The only journal that's not open access that we published in is my co-founder, Greg Gage, was invited to write an editorial piece on the case for neuroscience in a high school classroom for Neuron. And as part of the negotiation, I think that article is on. There's no paywall on that article, even though it's a Neuron article. Everything else is Advances in Physiology Education, which is open. The Journal of Undergraduate Neuroscience Education, which is open. Frontiers, which is open. PLOS, which is open. And the publication fees, I think we've paid a couple times. It's about $1,000, I think, and we've paid it. If you're on an NIH grant in the United States, they allow you to use part of the grant for publication fees to keep the article open. They also do offer discounts if the lab is under financial hardship. So people want to see your work published. So I don't think that's a very big issue. People want to help you. And also, we have a colleague who built a website called BioBricks. I think BioBricks or something like that. Maybe André remembers, where you could just put it online without not necessarily publishing it in a scientific journal. But that's what the comments I have to make.
Yeah. So I mean, of course, like what Tim said, absolutely. We also, like all of the things we published so far, they're all open access, and we also had to pay these fees, but there are different models for open access, right? And so what you're saying that as soon as the paper come out, it's absolutely free for everyone to read. It's called golden open access, I think. And then you have something that is called green open access, which is, there is a little period of embargo where this is not open access, maybe like 6 months, and then it becomes open access after that. Or there is a hybrid model where you can deposit the last proof of the paper into a public repository, and then the published thing is not by itself open access, but then the previous one, which is, the author's final version is. And so there are like different ways of publishing open access that doesn't cost a word. But I'm really not a specialist on this. Like I can definitely send links of like people that you should reach out to, or groups or things. But then nowadays you also have preprints, right? So everything that we've been doing, we also have been doing preprints. And they also help with the publication, because as soon as the paper is ready for submission, we deposit it as a preprint, right? And then we go online on Twitter or whatever, and then we tell the world that this is available as a preprint. And this helps in the sense that gets like a little peak of attention. And then whenever we write to the editors to consider the paper, we say, look, like we have this preprint, has been already retweeted or whatever, is getting like this X attention from people. And so you should consider it for your journal, because it is like worth reading. Because as you said, right, like the same time researchers have the pressure of having to publish this in peer-reviewed things, the journals have the pressure of actually putting out things that get attention, right? And then I don't know how it is for a lot of the different countries in South America, but as Tim said, a lot of these journals do have like waiver policies. The last time I checked, I think Brazil didn't have one. So I don't know about the other countries, because they consider Brazil to be like in a high enough stage that people could pay for them. But yeah, so if you can do like one of the many methods of open access, right? And if you can, absolutely not always do a preprint, right? And then if you can, do any of these methods of open access, right? Like not all of them cost a word, yeah.
And I wanted to add that when we first published our Spiker Box paper, we were trying to be cute, and so it was open source crowdsource. So to publish in PLOS, I think it was a $1,300 publication fee, and we wanted to pay it because we wanted to support PLOS's model. What we did is we actually put it on a Kickstarter, and this was in 2012 when Kickstarter was actually quite It was quite hot. And so we just, people paid like $1 or $2. Then our author contribution list in the article, we thanked all the Kickstarter contributors. So, I mean, there are creative ways to raise that money. Once you have a paper accepted, you'll find a way to get that money. I mean, people want to help you, you know.
So actually on the subject of papers and open tools, right? Cecilia asked on the chat, she would like to build a device to record her EEG signals and process them using open tools. But since they don't have an EEG in their lab and buying one is expensive, if she were to build that EEG and take the data and process them, etc., her question is, when I get results and I can publish a paper, would the publishers accept a paper that would use these, self-built tools to get the data, or would she get objections or difficulties? Now, what is your perspective on
that? I must disclose a conflict of interest. Backyard Brains does sell an EEG amplifier for $150. That is quite good and we're quite proud of. We do have the schematic on our website, so you can download the schematic and build the circuit yourself. I would be very, very surprised if a reviewer criticized your data based
Por favor,
on...
¿podrías darme esa respuesta en español? Porque
Sí,
es
obvio.
súper importante y me cuesta mucho entender el inglés hablado. Sí, escrito sí,
Okay,
pero
sí.
hablado es
Sí,
difícil. Y me interesa mucho tu respuesta.
Sí, no hay problema. Yo quise decir que mi empresa vende equipos para electroencefalografía, así que yo tengo un conflicto de interés, pero en nuestro sitio de web tenemos el circuito y tú puedes bajar el diagrama del circuito y armar el circuito por sí mismo y no es un problema. Y yo estaría muy sorprendido si fuera un comentario diciendo que ya tú armaste tu propio circuito, así no tenemos confianza en tu data. Es más increíble, en mi opinión, si yo leyera un paper donde las personas armaran su propio aparato. So, no debería ser una preocupación para ti, en mi opinión profesional.
Muchas gracias, muchísimas gracias.
No hay problema, no hay de qué.
Just to add one thing to this, em português talvez, I don't know, não sei se é melhor em português ou em espanhol, ou em inglês. Você poderia também, colaborando com alguém que tem o equipamento, fazer um estudo comparando o seu equipamento que você criou com um comercial, né? E aí você mostra num artigo que eles têm a mesma performance e os seus próximos artigos usando o seu feito no laboratório podem fazer referência ao artigo anterior, onde existe a comparação. Então você fala, olha, comparei com o comercial, funciona do mesmo jeito, e a partir de então agora, tudo que sair vai ter como referência esse outro artigo. I don't know if that makes sense. Or if I should repeat it in English. Sorry. Is it all good? Yeah.
Sí, ¿puedo agregar un comentario sobre eso? Otra cosa como estrategia para publicar es que si usás un EEG que sea open y otros grupos ya lo hayan usado, hayan publicado con eso, es un antecedente de que el equipo funcione y que otras revistas lo han aprobado como fuente de datos. Entonces, en vez de inventar uno de cero y además de ahorrarte ese trabajo, tenés la ventaja de que ya sabés que ese equipo funciona y que los journals lo han aceptado.
Bien, ok, muchísimas gracias. Realmente nos daría acceso a nuestro laboratorio a tomar datos con EEG, porque de momento nos habían prestado un EEG, pero eso implicaba ciertas cuestiones y ahora nos pidieron que lo devolvamos y nosotros no tenemos financiamiento para comprar un equipo de EEG, que es muchísima plata. Y entonces este tipo de herramientas nos permitiría, digamos, incluso vos tomar la información de otros que ya lo construyeron y poder incluso no armar un equipo, sino por ahí más de uno, y entonces tomar los datos que queremos tomar y armar los experimentos que queremos armar, que nosotros trabajamos con personas, no con animales, ¿no?
Bueno.
Bueno, so sorry to get back to the English. Actually, this brings a very important point, which is the language barrier that we all face from being Spanish speakers and having to train in English with very specific topics in mind, and having to get an education in English in terms of all. I mean, we study in Spanish, but we have to translate all of our work to publish in English, and we take courses in English, conferences in English. So there's this double thing. I guess people in Brazil also have this problem. And what is your take on having this information or these resources, especially with the educational and outreach? Is it possible? What are the ways to start making this possible and disseminate it in different languages? And if I may add to that a slightly different question, the remote aspect and the virtual aspect of educational resources, because maybe that is a way of having them simultaneously in many languages. I don't know, there's like an open question to discuss this.
Well, Africa has so many languages. I'm going to let André answer that one.
So, I mean, this is definitely something we experience quite a lot. So, for instance, in countries where, like a lot of the experience from countries in Africa is that you have 3, 4, 5, 10 different official languages, right? Depending on the country. And sometimes one of them is English. And in those countries, we do have like an easier time like communicating and so on. But whenever we had people from countries where one of the official languages were not, like local languages to Africa and were not English as well, but French, we had a big problem because like we couldn't like very well communicate. And we even had a group where 2 people from the same group could not communicate because one of them was a visiting researcher that didn't speak French, and the other one was a French-speaking engineer that didn't speak English. And so they were trying to build something together and didn't even speak a common language, which was, yeah. And so this is a tough thing that we have to deal with. And for us, what we've been doing is always having somebody from the tutors or from the organizers that speaks, at least one person that speaks a language that is not a common language from everybody else, right? As in, if there is a group that speaks French, then there should be somebody there who also speaks French, who's part of the organizing team. If you're talking about online things now, there are like many software tools that do live translation into like different languages, right? I don't know how good they are, but this could be a solution. But it is indeed like a tough problem, right? I don't have like I'm not happy with this answer in the terms of like I don't have a definite solution for it. This was one of the things that we want to do with Open Neuroscience, but we didn't find the time, which was to translate it to different languages. So here's a little shout out if anybody feels like translating, or it's not even about translating one by one, right? Like what we want to do is throw it into one of these translating tools like Google Translate and whatever, and then just later checking to see if the translations make sense, right? And so we could have like a whole Spanish version of Open Neuroscience, right? Yeah. So I don't have like a good solution for this. It's really a barrier. But indeed, if there were like more translations, then people would have the opportunity of learning more about specific terms and so on, right? Yeah. Yeah,
and for us, we were invited to Chile from a grant from the government, and so we used significant grant to hire a local translator to translate all our experiments. And we did the same when we came to Korea 2 years ago. So we actually just found someone who was had a science background, who liked Backyard Brains mission, and we just paid them for the work. So.
Just a word on that. We are doing this course in Spanish, right? And we wanted to invite people from abroad, like speakers like you, and we were really like we knew that we could have some problems with our students, and of course always with us, because maybe if it's not your native language, you cannot understand the whole, the 100% of what the other people, maybe you just understand the 80%, and that's fine, but we really wanted our students to understand everything, and we thought about including a translator, a person that translated like at the same time the talks, but we couldn't we couldn't arrange that. So we are recording these talks, and we will do the translation with the letters down, and so the students can have the possibility to re-see the talks, and maybe try to find the details that if they have missed them.
Sí, y si ustedes tienen más dudas sobre electrónica y circuitos, yo voy a escribir mi email de nuevo, y ustedes pueden escribirme como quieran. Si tengas más preguntas o si quieres asistencia cuando estás armando tus propios circuitos, yo feliz de asistirles.
Gracias, Tim. Y lo que decía Verónica era que iba a haber subtítulos en esta charla que vamos a subir al final, así que para que puedan volver a escucharla y leerlos. So maybe just for a final wrap up. Oh, yes, Marcos.
Yes, in line with what Cecilia asked before, have you found some problem to publish and contrast data collected with open tools compared to commercial equipment? I mean, you know that commercial equipment is calibrated and has to comply with certain regulations. So maybe there's some problem there. And other question is, how is the regulatory process with respect to open tools, to open equipment, hardware?
See, so I'll answer this, and then André can add something if he wants. So we get this question a lot. So the biggest thing that separates backyard brain skier from the big boys and girls is we don't actually know what the exact voltage is. We know it's around, 100 microvolts, 100 millivolts, but we can't tell you that this action potential is 80 millivolts because we're not calibrated, and all the resistors that might be slightly different. So nobody can publish using our millivolts using our work. But since neurons fire spikes, and you can just count the spikes and do a firing rate analysis, you can publish based on firing rate analysis, but you can't on voltage. And that's something that we've been wanting to solve for a number of years. And with the regulatory environment, you just have to send your equipment. If it is interfacing with humans, you have to send it to some institute to get certified. We had to do that in the United States, and we had to do that in Korea. They just inject a bunch of electric signals in it to make sure it doesn't, emit interfering signals, something like that. But if you're not building a device that you're selling and people are connecting their bodies to, the regulatory environment is not of a huge concern. It's only like when you're actually connecting to people that you got to worry about it.
So just to add a comment to this and to turn the question a little bit on its head, when was the last time a lab calibrated its PCR machine? Right? Like this thing has been working for like the last 10 years. And I'm saying this because I suspect, and like we're working on starting to work on a little project to test this, that a lot of the anecdotes that you hear from people saying, oh, this experiment works in this lab on the hands of these students, is because the machines are saying something on the display, but doing something else, right? Like, oh, if you're pipetting something and the pipette is not calibrated, although it says 100 microliters, is actually like 120 or like 105, right? And then like this variability, if you add up like the pipettes and the tubes and the machine and blah, 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 and the timers and so on, like this leads to experiments that only work like if you are hopping on one leg and have a tinfoil hat or whatever, right? And so the advantage of being open source is that you can, in principle, because you know how it's built and you know how it works, you could, before every single experiment, calibrate your equipment and then you know exactly what it's coming out because you calibrated, right? And so this is part of, I mean, I can share a bunch of these links, and I think a lot of them are in the presentation, but there are a lot of people working on this, right? And they say, like, other than the building instructions, you should have the calibration instructions for equipment shipped with your designs, right? So that once you build it, you know it's doing exactly what it's supposed to be doing. And the other thing is that there is a group in Germany, in Europe, that actually has contacted the DIN, which is the German Institute for Metrology, right? And they created a specification for open source hardware. So there is now a DIN spec, which is the DIN specification for open source hardware. And so if you're bringing something to industry and you're going to do like large scale building of open source hardware, now you have the specification that you should follow to get this DIN specification accredited to your piece of hardware. So this is like slowly becoming more and more like mainstream in terms of the industry as well. Yeah.
Thank you.
So for our closing question, Azul.
Okay, hi.
You have this great honor.
Thank you very much for the talk and for your work. And I was wondering, how do you envision open source in science in 10 years? And what about education? So it's like, I know it's a broad question, but I'd like to hear your opinion.
Andre, you go first this time.
I have a quick one. So I envision that people don't even know anymore if it's open source or not, right? Like you don't care because everything will be open source. And so it's not a question of like, you know, like and the point of this is that it is going to be so well documented, so well prepared, so well everything that it's just going to be like a turnkey thing, right? You could buy it from a company that is selling you an open source thing, and then you're just using it, and you don't even have to know if it's open source or not, right?
And for me, like I said, the vision of Backyard Brains is that academics is a circle, you know, or high schools, grad schools, universities. I think with this open source equipment that's easy, well documented, and easy to explain is allowing all educational institutions at all levels and globally to participate in the scientific process. So I think we're going to see a lot more involvement from not quote unquote non-traditional sectors and actual publishing data.
It's super, super nice.
Let's hope to continue down that road. So thank you everyone for coming. Thank you so much to the speakers.
We have one question, sorry, for one of the students, Natalia Soldi. Can we have?
It should be like extra quick. It's super late.
Sorry, it's a little
Go
bit.
ahead.
But I couldn't avoid noticing that in the pictures of your presentations, but the one of the Iranian girls, no, that one no, but the other ones, there was a lot of men in the pictures. So I wanted to ask you, like how the percentage of women, men, or the proportions are where you work, and if it's really like that, like more men than women.
Yeah, so in Backyard Brains, I think we have 15 people, and 3 are women. So that's something we should definitely improve. In terms of educational activities, I mean, I'm in high schools all the time, and that's just roughly 50-50. So that's just very normal high school. But yeah, I guess the organization could do a better job of recruiting more women. It's good criticism.
Yeah, and so just quickly, in our case for Trend, we normally get applicants in groups for the open library workshops, and they're at a rate of 20 to 80% like men, so 80% men and 20% women. And so in the application process, we encourage and we say groups that are composed of at least groups of 3 that are composed of at least 1 or more women, like are going to be given preferences. So in the end, the courses normally have a 50-50 ratio of men and women, right? And yeah, and so this is definitely something that is relevant. Yeah.
Definitely something we should all be aiming to balance out and to change. So thank you everyone. I will be finalizing the stream now.